Hey there, my name is Alexander Zajda, and I'll be presenting the work I did in partnership with the North Carolina Space Grant and NASA on designing and optimizing a concentrated flat plate solar collector for Martian habitation. So a little bit of background, restoring the solar thermal energy latently. Of course, this study is important because energy absorption and storage is going to be a huge roadblock to overcome for upcoming human colony on Mars. I'll be placing this collector at our Sea Mons on the Martian equator. We like this area as it's very predictable seasonal light intensity changes and already has available geothermal heating. And we look at some of the atmospheric and gravitational properties of Mars. We see it's made up of mostly carbon dioxide, very cold ambient temperature, and about a third of Earth's gravity. So we now look at the collector itself. We have mirrors outside the frame that are concentrating the incoming solar radiation onto this cover. Okay, the shortwave radiation gets transmitted through the cover, through this gap, and then gets absorbed into this plate, and then is transferred into the phase change material itself. This transparent cover, we want opaque to long wave thermal radiation coming back up from the plate. And so we make it out of aluminum dipped zinc oxide glass. And this absorbing plate, we want as high absorptivity as possible for the short wave radiation. So we make it out of cobalt coated copper. And then we focus on parameterizing and optimizing the phase change material itself. So a little bit of theory. I'm not going to go through this too in depth because I'm living on time here, but we have the absorbed energy minus the lost energy is equal to the amount of energy we can use to melt the paraffin, the phase change material. And we see the absorbed energy is a function of the concentration ratio, which we talked about earlier. It's going to be a value of 20 in this case, which is a realistic value and even on the safe side. And then we have our convective and radiative losses from both the plate to cover and cover to ambient. We model the heat transfer within the PCM itself by ignoring advection, which is safe for a flat plate on Martian soil where the gravity is about a third, so we have a much lower body force. And we model the phase change using the apparent heat capacity method in COMSOL. So we look into optimizing the PCM, we look at paraffins. We like these paraffins as they melt in between 30 and 60 degrees Celsius, which is a good living temperature. We look at some of the thermal properties, and then we actually do our first computational experiment here, which is seeing which paraffin can store the most amount of power during a Martian day on an infinite plate. And so we see here, well, the nonadecane melts farther, but it only stores 10,000 kilojoules versus docosane, which stores 12,000. We say, why is that? Well, we see nonadecane has a very low latent heat diffusion. So we obviously want to maximize that. Now, the other thing is icosane has a higher conductivity and a higher latent heat diffusion. How come there's less energy stored? Well, it doesn't melt as far. And how come that is the case? Well, docosane actually has a much lower heat capacity, which is a good thing in this case, as it takes less energy to change a particle of the material by a degree Kelvin, so it reaches its melt temperature quicker and thus stores more energy latently in its phase change. So now we look at optimizing the thickness ratio. We see here the thickness ratio, of course, is the ratio of the thickness of the PCM, which is paraffin in this case, to the thickness of the plate, gap, and cover, which is 15 millimeters. And we see here the optimal distance is when it's fully melted. It just fully melts at the end of a Martian day, right? Any more, and we're wasting some of that energy and just heating up the liquid. Any less, and we're not fully melting all available paraffin and just heating up the solid. And we see here we store about 469 kilowatt hours and 100 plates. We see here the maximum collector temperature is reached at 9 Martian hours. And then at 12 Martian hours, the maximum temperature decreased, but we still have residual heating within the paraffin itself because there still are those temperature gradients. And we see here why it's important to optimize the thickness ratio. So when we optimize the amount of material we use, we save a lot of money. Of course, it's expensive to get things to space. It's even more expensive to get them to another planet. And so it looks like we'll save at least 3 times. Just using back of the envelope calculation, save at least 3 times by optimizing from that initial long plate. So in conclusion, thank you to North Carolina Space Grant for allowing me this opportunity. Please, any questions, email me here at awz@duke.edu, and I'll see you guys in space. Yeah.